Okay, after that short hiatus, let's continue by bounding the minor arc terms. This will be a simpler proof, but first we need to define what they are. I'm just going to take it, and it's the same integral we had before, but just restricted to the minor arcs. Nothing big there. And the convolution operator is defined by multiplication on the Fourier side, once again, which is just multiplication by this function. Okay, much like our first differences, how we defined our first differences and our first approximation. So, to remind you, Weil's inequality, this is going to be how we prove it. We're going to use two ingredients, Weil's inequality and that main L2 lemma. So what was Weil's inequality? Well, just for quadratic polynomials, if we had a quadratic polynomial tn squared plus cn, then we had this bound, well, I guess for the absolute value, technically. And the important thing to point out here is that this bound is uniform on the linear part C. It doesn't depend on what C is in R. All it depended on was this rational approximation to the point T, which is the quadratic part, right? T is being multiplied by n squared. Okay, and what was it? Well, if Q is about R here, then basically what this was saying is this is R to the 1/2 plus epsilon. And you have a bound depending on epsilon, some constant depending on epsilon, okay? But again, this is uniform in all C. So it's saying we have roughly square root cancellation uniformly in the linear part. So now we just apply that main L2 inequality, right? Just directly followed by Weil's inequality. Because remember, this main L2 inequality turns this into a supremum over all C. And that supremum over C is what? Well, it's just this right here. We look at the sup over C in the torus, right? And that moves, oh, sorry. Let's be correct about this. The supremum over lambda means that we want to bound instead the sup over C on the torus, the integral over the minor arcs of HRTC with respect to T. We take absolute values to destroy any potential oscillation coming from this factor. And when we do that, we just apply Weil's inequality straight to this. Well, this was an exponential sum. As the same one here, but with a smoothing factor. And I didn't go over how to do this, but you can prove this form of Weil's inequality with the smoothing factor just the same as you proved this version, as we proved this version in the first part of the course. So then we just see that plugging in this term right here, oops, d times, because this is a tensor product, this exponential sum is a default tensor product, we get the claimed bound right here. Great. And yeah, this required, remember, if you're on a minor arc, Q is greater than Y. So that's why we get to replace all the Q's here with these factors right here. And as a corollary, taking our choices of X and Y, as I said they would be earlier, as well as our choice of R, we end up getting this bound for the maximal, the dyadic maximal function associated to the minor arc error terms on L2. You notice that this is almost lambda to the d over 2, which would be square root cancellation. But there's these deltas and epsilons that we've lost. Oh, there's little, this also depends on epsilon. So this is going to force us later on to choose delta sufficiently small, after, of course, choosing epsilon sufficiently small. Great. Any questions about that? Is much like before in the first part, all the work is in Wiles inequality, and we just sort of get to apply that as this nice big hammer, wham, that part is done. And the more work is going to be in the major arcs. All right, so what's our second approximation? Well, that's going to be given to us by completing the singular integral. Okay, so remember B1 was defined so that we had this integral actually being over a of q. Sorry, the arc I of AQ. All right, but now it's actually going to be over all of R. And so that means we have to handle this difference right here, which is of course R minus it's the complement of that arc inside of the real numbers. So we proved this previously, or the analogous bound for this when C was equal to 0, C was equal to 0, was proven by stationary phase, not non-stationary phase, not integration by parts, but by stationary phase. And for that, we have this following proposition. Okay. I claim that when I look at the Fourier transform of little hr at a point C, and I take the supreme over all possible C in the torus. So here I'm identifying TD with -1/2 to 1/2 in every direction. And I integrate that outside of that little arc around 0. I get this bound. Okay. And that's true for every major arc. Remember, I'm done with minor arcs now. I don't have to worry about those. I need to worry about the major arcs at this stage. Great, so how do we prove this? Just bringing up my notes. Okay. Let's start by writing out what the integral is. So I have the integral over R minus I of AQ. I'm fixing AQ, right? Fix AQ in the major arcs. All right, and yes, and I have the sup over XC and TD of this Fourier transform. So this is actually equal to, I want to write out what that Fourier transform is. This is just equal to the integral over R minus I of AQ. And then I take the sup over all the points C. Absolute values of the Fourier transform written out as its own integral. So that's an integral over RD. And now I have phi of x over R, e of x squared t plus x dot c. And that plus looks like a lot like a t. Great. Absolute valued again, integral to the t, integral over t. These integrals inside here are tensor products. So it's actually equal to a product for one in each direction. That's because the function phi is, and this is a sum, and this is a sum. So that turns into products. So we have for some phi naught, xi over r, e of t xi squared plus xi ci. And yeah, so we are going to reduce our analysis to just proving to finding a bound for the one-dimensional integrals here. Okay. Now, before doing that, I am going to complete the square to handle this integral, this one-dimensional integral. Okay, let's complete the square. And so what does that give us? I'm just gonna, this gives us the fact that the integral over r of phi naught xi over r of e of t. Now, it's a little bit tricky to write, but this will be xi plus, I would like to just say xi over 2 squared. But that's not quite right because there's no factor of t inside of here. So I actually need to divide by the square root of t, but t could be negative. So I have to be a bit more careful. The way I'll do that is I'll actually just write it as 2 times the square root of the absolute value of t times the sine of t. All right, and then this is, so that, and minus, of course, t xi squared over 4t. That's just completing the square there, and I need to, oh, I should have said this is an integral over dx. So this is an integral over dxi. So this is an integral over dxi.
Is that an absolute value of t in the denominator?
Yes, that's the square root of an absolute value of t, and then times the sine of t.
Yeah, so when you square that, you get 4 absolute value of t.
Oh, you're right. Wait, yes, you're right. I times, well, okay. I times the sine, is that right? Okay, depending on whether or not t is positive or negative, this sine function is just going to do it so that it corrects that. And sine function now may actually be I or minus I or something like that. Are you happy with that?
Yeah, I think what you're supposed to do is put a plus or minus t out front.
Over here.
Yeah, so that you don't have to deal with this issue.
I think I want it. I think I want the plus or minus here, actually. Yeah, I think I want the plus or minus here. And you choose minus to compensate for the sign, if there is one, or plus. So there is a choice of plus or minus, such that this is true. And this should also be a minus or plus. Right here, minus or plus.
Yeah.
The point being now that when I take the absolute value, this term, which does not depend on x, is taken out of the is disappeared by the absolute value. Okay, so this is just equal to the integral over r phi naught of xi over r e of t xi plus or minus ci over 2 root absolute value of t squared and then dxi absolute value. Excuse me. So yeah, so now I just translate that integral, right? This is equal to, by translation, well, minus or plus the integral of e t xi squared dxi in absolute value. And even though this is shifted, this function here is shifted now, our bounds from before apply. So our bounds from the first part apply, the stationary phase bounds. And what we said before was that this is at most, I think we said this is at most 1 plus t minus 1/2 as t goes to infinity. Right, so we had before, we had a suprema over c we had to worry about. But by completing the square in translation, we don't care what that c is anymore. And now we have a bound for this, this integral that's going to have something that decays with t. So altogether, we have the integral over r minus I of aq of h r t, the Fourier transform, sorry, absolute value, xc, oh, and I need a sup over xc here, is at most the integral from r minus I of a over q, 1 plus t to the minus d over 2. Because this was a one-dimensional bound, and I had a d-fold tensor product of them, right? So that's why I get the factor of d here. Okay, again, we know how big I of a over q is, and roughly how big it is, and that is centered at the origin. So we actually get to say that this is at most the integral of minus c over qx for some c that does not depend on q or x, all the way to infinity. Oh, sorry, that's a plus c, plus c. And oh yeah, of what? Of this 1 plus t to the minus d over 2 dt. I'll ignore this factor of 1 and just bound this by usual calculus. It's going to be at most whatever, depending on that c, 1 over qx to the 1 minus d over 2. Okay, and that is that's the bound I claim, just because this is equal to qx to the d over 2 minus 1, right? Great. So we get to use this. Sorry, were there any questions about that? Any further questions? I had this sign thing that I had to worry about, but that wasn't really an issue. And then the other trick or observation really in this case is that the uniformity in the bound we had for these in our first set of notes in the first part of the course, uniformity and shifting by c and or c over t square root of t. Okay, also everyone is happy with that. So we get to deduce what's the second major approximations. As soon as we have 3 or more dimensions and we have an arc I of a over q, if we set our Fourier level to be something large and we pick our dyadic window for some lambda and our r accordingly, then we get this bound for the dyadic maximal function of the second of the error term in our approximation to the major arcs. Where does this come from? This differs. Before we said qx. So for that one, for this, what do we have? The integral over r minus I of a over q, sup over c, h r t c Fourier transformed. We had this bound the difference between this and this here is that d, little d to aq lambda c is a sum of Gauss sums, right? Localized by these things. So qc minus m hr t c minus m over q dt. Oh, integral I a over q. And this Gauss sum is at most 2 to the d q to the minus d over 2. So that compensates for this power of q, leaving us with this bound as claimed. Cool. And as I've noted here, it's just the main L2 bound and the Gauss bound. So as a corollary, choosing our thresholds, as I've indicated before, what we find is that we have something, this should be with a factor, a constant depending on delta as well. We have basically square cancellation again. We have that we have this bound for that maximal function as soon as we make the right choices. Okay. This is the same size basically as the one we saw for the minor arcs. Before we had a delta plus an epsilon, but both delta and epsilon are so small that it's not, we just choose them small enough and it'll be the right thing here. Great. So let's go on to the singular integral. I mentioned this towards the beginning of the previous video, that we know what this is from the first part of the lectures. We know that this is the Fourier transform of the spherical measure, or at least the spherical measure we defined before. Okay. However, we didn't normalize it. You have to recall this from the previous lectures as well. What we need to do, what we have is this factor of lambda to the d over 2 minus 1. Right, the d sigma, we were defining those isotropically, so that d sigma of r for a radius r, when you look at this Fourier transform xc, it's just d sigma of rc. Okay, but when c is equal to 0, we need to remember that we had basically this many points on our, as far as the number of ways to represent an integer as a sum of d squares. And when this is at 0, this is just telling us it's the mass of the sphere, of the unit sphere, which is O of 1. It's actually something explicit depending on the dimension. It's some product of gamma functions that that is a very common exercise in calculus, freshman calculus, but I'm not going into now. And what this tells us is that when we look at the second approximation, it has this shape down here at the bottom, right? I am actually getting what I was claiming in the approximation before for each a over q. But at the moment, my sum is only over a finite range of a and q, whereas my approximation was over an infinite range. Was I supposed to prove something here? Don't think so. No. Okay. Were there any questions about that? Remember, this spherical measure is a delta distribution, and it's compactly supported in this Fourier transform makes sense. It had this nice decay as c goes to infinity. It decays like c to the 1 minus. Yeah, I'll just write it down. It had that decay, which we used in the de Proust-Stein spherical maximal function, or the bounds. So as I said, the last part, sorry, as I said before, that so far we have a finite sum over AQ, over fractions AQ, and now, but the approximation formula has an infinite sum. So what are we going to do? Our last error term, our last remainder is going to be throwing in all of those remaining fractions. We only, because of the minor arcs, we only threw in all the fractions with height up to, say, y. And we have to throw in fractions now that have height that goes to infinity, but is at least y. Okay. And when you make the right choices as before, you just get these bounds. So this q to the minus d over 2. So for each of the terms in the approximation, this q to the minus d over 2 is coming, as always, from the square root cancellation in the Gauss sums. And this part is coming from this, so many pages away, is coming from our normalization, or lack thereof, for the spherical measure. Right, as lambda varies between big lambda and twice big lambda, this factor up to constants is always basically big lambda to the d over 2 minus 1. That's all I use down here. And now summing overall a coprime to q between 1 and q, I lose a factor of q, and then I sum up overall q greater than y. I lose another factor of q. That gives me that this is at most, depending on some constant, depending on the dimension, this bound, y to the 2 minus d over 2 times lambda to the d over 2 minus 1. Great. That is just applying the triangle inequality to remove those double sums outside. Very simple there. Really any questions about that? All right, assuming not, I'm going to wrap up with what is the error term we had. Just collect all the terms and record the bound that we have for it. Okay. Remember, the error term was formed from these. Oh, that should be a y. So on the major arcs, I had all these differences. I had my first approximation and my second approximation for each a over q on the major arcs. And then I completed my singular series. So that meant I had to sum over all fractions of a big height for this second approximation, plus the minor arc term that I had. Now, when you go back through the above and you take the worst, you plug in the error terms at each step, the worst one you get is that you can find for every epsilon, there exists some constant, such that for all big lambda, that dyadic maximal function for the error term is bounded on L2 to itself by lambda to the d over 4 plus epsilon. Right, and I can take epsilon as small as I want. So this is pretty, so this is roughly of size lambda to the d over 4. But that a little epsilon will be something we have to pay attention to later. Magyar Stein Wainger proved their approximation formula. It takes the exact same shape as ours, but they use theta functions to get slightly better estimates in the error terms. In particular, because this is quadratic, you can use the Kloosterman. Well, no, because of this is quadratic, you don't have to use minor arcs if you resort to smoothing by Gaussians and using theta functions. Then without the minor arcs, I don't have to use Weil's bound. That's great. That's where I had one source of an epsilon loss. The other epsilon loss came from having to choose, basically when I optimized some parameters, I had to choose x to be a little bit bigger than r and y to be a little bit smaller than r by some powers that are slightly bigger than 1 and slightly less than 1 for r respectively. And optimizing those two against each other also led to another epsilon loss. But you just get to choose those. You don't have any minor arcs, and that part disappears as well. And you'll find that the approximations otherwise were sufficiently good. So that didn't matter. But that's in their treatment. Here, we're going to not be so special with our smoothing function, do things a bit more generically. and we're going to lose that epsilon, but it's going to be fine to recover their theorem. Okay. So if there are any questions, go ahead and stop me. Otherwise, I think that is all for today. All right, I'll pause there. Thank you very much.